All right, something tells me this is not going to be the last time you're going to see this standard from me, but this is the Eikonal equation standard again. And obviously we start here with the wave equation, and the deal with that is so this looks familiar, that part, but this part right here, that is so this is the Laplace, excuse me, the time derivative has already been taken here, and we're putting in this in terms of n, which is index of refraction, omega, and then and c. Um, and the reason we can do that is that we know, because first of all, the C gets rid of a few terms. That gets rid of those the epsilon naught and the mu sub naught terms, and then N can also then can substitute out for a time. So it's usually omega t. So and then n in conjunction there. So we get the interesting thing here too is that this is also, so this is a spatial equation here. So it's a function now of r, n of r, e of r. You can see that in each of that. And the reason for that is that we are suggesting that in a setup. So I drew just a mock-up. I think this is a little bit better than what I did before. Is that if we have a wavefront, the deal is that this could be changing, that the substance, whether it be glass or something, a ray could be going through a different index of refraction at a different spatial location. So we're taking that into account. So it's n of r, e of r. So given the given position. Now, anyway, so what I'm going to show here with the math is that, as we can see, we have wavefront 1, wavefront 2, wavefront 3, and then simply the perpendicular direction of travel arrow is simply the gradient, kind of like voltage is the gradient of electric field, and what we have here is that we have the gradient here is used to determine where we're going to find the next wavefront out here, and then going further and further out. It's not as simple as a plain wave anymore, and so and the shape of this front can very well change. Okay, so back to our, here we go. And that's what that's showing there, is that, so right there, I wish I could get this bigger. I think I can. Nope, that's not it. But anyway, what that's showing is that you've got your wavefront, and then your gradient, R of R is, that is each of those red arrows there. So anyway, so we've got our, so they're suggesting this is a solution to the wave equation, or to this equation, that looks very familiar. So I will take it as I think that has a good shot of being right. Where obviously K, this is, we've already learned these relationships. So obviously 9,4 is just, it's a tautology, and then that we substitute that in, and that's what gives us 9,5. And again, there's a whole red box here because this Laplacian is hard, and there was, like, I think you had like 2 or 3 screencasts that just talked about that. But essentially, what we're doing here is, so we're calculating the gradient, and then we're calculating the gradient, and then we're calculating the gradient of the gradient, to get all of this. So it is a real mess to do. Obviously, to calculate that, as we do with the plane waves equation, R is actually, it actually stands for x, y, and z, and so then and that's why here you've got an x hat, a y hat, and a z hat. But fortunately, we find out this right there, and that, unfortunately, I know what that means now, rather than kind of guessing in my last screencast. So anyway, again, this relationship is always true. 1 over k is lambda over 2 pi. We're just saying that that's going towards 0. We're saying that that we're dealing with wavelengths that are or that the change in wavelengths is very 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 short. On a surface because the change in the surface is it's very gradual. So we're assuming that that the wavelength can go towards 0, and I guess I think that's the best I can say about that. I wish I had better words to use to say that, but anyway, mathematically that's very convenient because you see all of these 1 over k terms. Where were they? Well, there we go. All of those, which are ugly, 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 but those now go towards 0. So then that leaves us with what is the Eikonal equation, which is this right there. So it's the gradient of r equals n of r, and then this s of r is just it's a pointing vector, or it's so it's pointing in the direction of the gradient. So which is these lines right there, those arrows there. So what this is, though, this is really good for telling us which direction this will go. But this is only a directionality equation, as far as I can tell. It says nothing about where we're going to end up. And that is where Fermat comes in. Fermat is saying, after a certain amount of time, where are you going to be? So then we've got Fermat's principle. And Fermat's principle is essentially what it says is that we take the path. We take the fastest path. A ray of light's always going to find the fastest path, which is kind of interesting. I guess until now, I took that as just obvious, but mathematically here we can derive that. And I guess when I first looked at this, I was like, why in the world are we taking the curl here? Because it's like, why? I mean, I mean, it's not one of those things that would be so intuitive to derive this, but we're taking the curl of the Eikonal equation, which was there, and we take the curl of it. But we do that so we can use Stokes' theorem, and Stokes' theorem relates the curl, or what it's doing, and I guess I'll take a moment here and I will explain that here within Paint. Oop, that's from another assignment that you should be getting here. Anyway, so we've got this we've got this surface there, and then each little infinitesimal component, and I can make little boxes there. Each of these little boxes here have, oopsie, let's try that again. But each has a certain amount of curl in there, and I wish this was working better, but it's not. But anyway, but what it's saying is that the individual components of the curl that make up the area of this whole box can be added up. And Stokes is saying that is the sum of the circulation all the way around the surface of that, which is kind of interesting. So anyway, that's all we're doing here. Is now instead of doing an area integral, now we're doing the perimeter contour integral around the whole thing. How does that relate to this picture? Well, because if we have light going through a surface, and we're suggesting that it's not going in crazy loops, but instead of it's going straight, there should be 0 curl. So let's see. Do we convert that to back? Well, here we go. The minimum. We're going for the minimum amount of. Let's see. So we're going for the smallest amount of distance traveled. So clearly we are trying to see which one we're trying to see which will have the least amount of curl over time. So that is optical path length is the path integral n dot dl from point A to say point B. So there we go with the conclusions that the true path that light follows between 2 points is the one with the shortest optical path length. And that the index can vary, obviously, with respect to position, which as a result, it's time dependent, not spatial dependent. So, depending on it, we may not be going in as we may not be travel. There may be